Hey guys, so today, instead of doing problems of the day like I usually do, I'm going to be doing a run through of this test, and yeah, I'll try to see how far I get. And so this test is 75 minutes, and it has 25 questions, as it says right over there. So I'm just gonna set a timer for 75 minutes. Okay, 3, 2, 1. Okay, I set the timer, and let's start the test. Okay, first question. A 600-meter river flows directly south at 4 meters per second. A small motorboat travels at 5 meters per second in still water. Oh, that's how fast it is in still water. Okay. And points in such a direction that it will travel directly east relative to the land. Okay, so for this one, it's actually just basic vectors. So that's the direction they gave us. They said it travels at 5 meters per second. But now there's the river pushing it 4 meters per second, and so we should get a right triangle, and this should be 3 meters per second then. And so it's asking how much time it takes to cross the river, and so that would just be 600 meters over 3 meters per second, which would just be 200 seconds. And so that is D. Alright, next one. A car travels directly north on a straight highway at a constant speed of 80 kilometers per hour for a distance of 25 kilometers. The car then continues directly north at a constant speed of 50 kilometers per hour for a distance of 75 more kilometers. The average speed of the car during the entire journey is closest to blank. Okay, so we know that distance is speed times time. Speed is distance over time. And the total distance is just 75 plus 25, so that's 100. And this is where it gets a little tricky, so we have to divide this into two sort of sections, since he goes at different speeds for like the 25 kilometers and then the 75 kilometers. So for the time, so since using this equation we get time is equal to distance over speed. So what we can do now is we have 25 kilometers over 80 kilometers per hour plus um, 75 kilometers over 50 kilometers per hour. And give me a sec, I need to get my calculator. Okay, so now I got my calculator, and let's plug that in. So it's 100 divided by the quantity of 25 over 80 plus 75 over 50, which should give us about 55.2 kilometers per hour. So A is the correct answer for this. Okay, the force of friction on an airplane in a level flight is given by uh, the friction is equal to kv squared, where k is some constant, and v is the speed of the airplane. When the power output from the engines is p naught, the plane is able to fly at a speed v naught. If the power output of the engines is increased by 100% to 2 p naught, the airplane will be able to fly at a new speed given by blank. Well, formula for power is force times velocity. And in this case, they already gave us the force, which is friction. And they said that was kv squared times velocity would be kv cubed. So we know that the power is directly proportional to v cubed, since k is constant, as they said right here. So then if we multiply p times 2 to get 2p, we have to multiply v by the cube root of 2 to double this. So then the cube root of 2, okay, I need to plug this in. Calculator's a bit slow. Okay, we're getting about 1.26, so this should be our answer. Alright. Oh man, I'm not very good at these ones, but I'll try. A 2 kilogram box is originally at rest on a horizontal surface where the coefficient of static friction between the box and surface is mu sub s, and the coefficient of kinetic friction between the box and surface is mu sub k, which is equal to 0.9 mu sub s. An external horizontal force of magnitude p is then applied to the box, which is the following is the graph of the acceleration of the box a versus the external force F. And also the formula for static friction is that's less than or equal to mu s times n k. Okay, so first we could split it up into two parts, I guess. So one where the box is not moving, and obviously when it's not moving, there's no acceleration. And then at the second it starts moving, the kinetic friction. Sorry, I lost my train of thought. The kinetic friction is less than the static friction. So when it's not moving, we know that the acceleration is 0. Yeah, and then wait a second. Okay, and then so for kinetic friction, they said that it was equal to 0.9 times this, and since it's flat ground, we can change it to this. The acceleration is just the sum of forces over mass. It's p over mass minus 0.9 mu sub s times g. Yeah, these all look pretty similar. Actually, so I have an idea. So here we can see that the y-intercept is clearly negative. Okay, so we can immediately rule this out since there isn't even a period where the acceleration is 0. For the same reason, we can rule this out. And so that leaves us with this, or this. And here we can see that the y-intercept would be positive, but then, as I said here, it would be negative. So that leaves us with either A or C. And I believe it's A, because usually with these types of problems, there's like a vertical line. I think that's like when it's the instant where the box starts moving, and C does not have that. Okay, 470-gram lead ball. Actually, I want to convert this to kilograms. So that would be 0.47 kilograms. Is launched at a 60-degree angle above the horizontal and initial speed 100 meters per second directly towards a target. Blah 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 blah. Okay, I'm not gonna read all of that. I'm sure you can read it, but ignoring air friction, by what distance does the lead ball miss the target when it hits the cliff wall? Okay, so basically it's asking us to find what height it reaches by the time it travels this distance. and then we can find the difference between this height and the height of the target. And yeah, okay, so for distance, we know that this is 60, so then this is really just 100 cosine 60, so that we know that this has to be, oh wait, okay, I saw the velocity, or speed, so I thought it was 50, but this is the hypotenuse is 150 meters, so this would have to be 75 meters. And we know that there is no acceleration in the horizontal direction since it told us to ignore air friction. So we can say then that 75 is equal to V naught cosine theta, or in other words, the horizontal component of the initial velocity times t. So t is equal to 75, and let's find V naught cosine theta. So V naught is 100 meters per second, and 100 cosine 60 is, well, it's just 50. And so we get 1.5 seconds. Okay, and now for the height. And this time we do have an acceleration. So now it would be V naught sine theta. Okay, H is equal to V naught sine theta times T minus 1 half GT squared. Okay, and then now it's sine 60, which is rad 3 over 2. So, and rad 3 over 2 times 100, it's just 50 rad 3 times 1.5 minus, well, G is approximately 10. 1.5 squared is 2.25. 10 times 1 half is 5. So we get 5, 2.25. Okay, and I'll just plug it in right now. And I'm getting about 118.6 meters. Okay, and then so this is 150 meters. This angle, as the problem said, is 60 degrees. And I'm assuming this is the 0, so I'll just draw a line here. Yeah, so this is 60, so 150 sine 60 would then just be 75 rad 3. So the target's height is 75 rad 3. And I just realized that this is 75 rad 3. So I didn't even need to put in the calculator, so I kind of wasted time. So then 5 times 2.25 would just be 11.25 meters. So the answer is E. Okay. 3 trolley cars are free to move on a one-dimensional frictionless horizontal track. Car A has a mass of 1.9. Sorry about that. 1.9 kilograms and an initial speed of 1.7 meters per second to the right. Okay, I'm not going to spend time reading it. So I'm just going to highlight all the important stuff. And 1.3 kilograms originally at rest. What is the velocity of the center of mass of the system 3 cars after the last collision? So this is our system, and we know that, well, the sum of forces, or external forces, is equal to instantaneous change in momentum with respect to time. And since everything is one-dimensional, it's traveling horizontally on a frictionless track, we don't need to worry about gravity since it's only vertical, and the track's frictionless, so there are no external forces acting on the system, which means that momentum must be conserved, and momentum in this case can also be written as mass times the velocity of the center of mass. So the velocity of the center mass initially should be the velocity of the center of the mass after the last collision as well. And so we can actually find that by multiplying each of the masses to their respective velocities and dividing by the sum of all the masses. So first we get 1.9 times 1.7 and minus 1.1 times 2.5 since it's traveling to the left, and cart C is at rest, so we do not need to worry about that. So then adding up all the masses, we get 1.9 plus 1.1 plus 1.3, and I have to plug this in. So 1.9 times 1.7 minus 1.1 times 2.5, all of which is divided by 1.9 plus 1.1 plus 1.3, and this should give us 0.11 meters per second. So the correct answer is A. Okay. So we have these cars on a long frictionless track, and shouldn't have done that because it's harder to read, but whatever. And these are the masses of the carts, and cart A is originally at the 0 mark moving towards cart B with a speed of V0, and the other two are at rest. And assuming all collisions are completely inelastic, what's the final speed of cart C? So since it's elastic, we know that A collides with B and they stick together, and then the AB system collides with C and everything sticks together. So then we have M V0 is equal to M plus 3M plus 9M V final, and this is just 13M, so V final is equal to 113 V0, which is also equal to A. Okay. And this one is a bit trickier. So for this one, I'll split it up into two phases, and phase one is where card A hits card B. And yeah, so just this formula, it's a bit tricky to memorize, but basically, if you have two systems, or not systems, two like components of a system, and they collide elastically, this formula tells you how to find the final velocities in terms of the masses and initial velocities. And so first we're going to look at the collision between card A and card B, and we want to only find the final speed of card B. And so the formula for that is actually just I believe it was m sub 2 minus m sub 1 over m sub 2 plus m sub 1 times v sub 2 initial plus 2m sub 1 over m sub 2 plus m sub 1 times v sub 1 initial. Okay, and then we know that b is initially at rest, so we can actually completely disregard this left expression and only look at this. And the massive cart 1 is just m's, and the massive cart 2 is 3m. And so the numerator is 2m, and denominator is 4m, so we get 1 half. So we have v0 over 2, since this is v0. Okay, and then, yeah, so now we have to look at the second set of collisions, which is between cart B and cart C. And we actually use the exact same formula again. And since cart C is initially at rest, we don't need this expression, as I said earlier. So we can write this now as v sub 2 final is equal to 2 times this plus this times v sub 1 initial, which we already said is this. So v sub 1 initial is just v0 over 2. Okay, and we can plug in the masses into here. So the mass of cart B is 3m. So for numerator we have 6m. And then mass of cart B is, yeah, said 3m already. And the mass of cart C is 9m. So we get 1/2 again, so we should get V naught over 4. A 0.65 kilogram ball moving at 5 meters per second collides at a 0.7 yada yada yada. Okay, so 0.65 5 meters per second. Interesting. So it says that the other ball moves off with a speed of 4 meters per second. Yeah, okay, so. And then it says that the original ball moves at a right angle to the final direction of motion. Okay, so maybe I'll say that it moves 4 meters per second here. And then this has to move at its final speed at 90 degrees. And what is the final speed? And actually, you can see that this is just the Pythagorean theorem, since 3 squared plus 4 squared is 5 squared, so this is just 3, I think. And yeah. Okay, let the change in total kinetic energy be defined by delta K is K final minus K initial, where K final is the total final kinetic energy, and K initial is the total initial kinetic energy. Which of the following is true? It's referring to the previous problem. Yeah, I'm not quite sure how to do this one. Okay, I think I'll get back to this one later. Okay, a sphere floats in water with 2/3 of the volume of the sphere submerged, and it's placed in oil with 3/4 the density of water. What fraction of the sphere would be submerged in the oil? Okay, so first we have the sphere in the water, 2/3 of it are submerged, and we have gravity, and we also have the buoyant force, and it appears that it's floating, so that means that the forces balance each other. And so the density of water, so for the buoyant force, the density of water times 2/3 the volume of the sphere, whatever it is, and times g, which is just equal to the mass of the sphere times g. And you can rewrite that as 2/3 times the density of water times g times g. And now it says that the oil has 3/4 the density of the water, and it floats in the oil. What fraction of it is submerged in the oil? Okay, so I'll just do a question mark to represent the fraction times g, and this is once again equal to mg. And so to find this, we can actually just divide this by this, and so we get 2/3 rho sub w times vg, and so the question mark would be 3/4 over 2/3, which is 3/4 times 3/2, and that's not right. It should not be over 1. Okay, let's see. Actually, no, let's just set this equal to 2/3 this, So 3/4 times the question mark is 2/3. We multiply both sides by 4/3. We get that this is 8/9, and this would have been 9/8. So I somehow flipped something, and so this is C. Okay. Pendulum consists of a small blob of mass M that attached to a fixed point by a string of length L. The pendulum bob swings down from rest from an initial angle of theta max less than 90 degrees. Okay, I'll just draw it out, I guess. And let's pretend that that's theta max. Okay, first of all, the magnitude of acceleration is constant for the motion. No, it's not yet. So that is basically right when it's about to go from theta max. That's when it's the highest. I think it's always directed towards the center of the circle. That would be true if the speed was constant, but that's not the case. And, and yeah, so that would be true only if the speed's constant. The magnitude of the acceleration is 0 some point during the pendulum swing. I think that might be true. The acceleration to the bottom of the swing is vertically upwards. Well, I know there should be a tangential component and a radial component, but at the bottom of the swing, I don't think it would be accelerating. So I think this could be true as well, I guess. The magnitude of the acceleration at the lowest point is g. Well, it's not falling since we have the tension, so it's either C or E, and I think for now I'll skip this. Okay, consider the pendulum bob when it's at an angle of theta is equal to 1/2 theta max on the way up. So it's moving this direction, and yeah. Okay, so first of all, there should be a tangential and radial component to the acceleration, and we know that it should be decelerating since it eventually stops when it reaches here. So since it's decelerating, the tangential component of the acceleration should point somewhere like this, and the radial component should point towards the center, and so the resultant of that should look something like this. Okay, so far, this is wrong because it just has a radial component. This is not pointing the direction, it's not pointing anywhere close to the direction we want. Neither is this, nor is this. And D, yeah, it looks like it's pointing the direction, so D should be our answer. Okay, a 3-meter long massless rod is free to rotate horizontally about its center. Two 5 kilogram point objects are originally located at ends of the rod and are free to slide. Yeah. Okay, so we have two, and they're point objects, so I'm just going to draw it like this just so they're easy to visualize. And we have another one here. Okay, and then there's a rope that connects them. And the system's rotating at 4 readings per second. Okay, so if we have a top view of it, it looks like this, and it's rotating, and the rope is keeping them from flying off. And what would make them fly off is this fictitious force known as the centrifugal force, not to be mistaken for the centripetal force. And the magnitude of that is m. And since we're using angular velocity, I'm going to use omega. So m omega squared r, and it's actually the same formula as centripetal force, but the direction's different. So this time it points really outwards. And since there are two masses, then the tension would be, I guess, 2 times 5, and omega squared would just be 16. Okay, and then it's 3 meters long, so radius should just be 1.5. So that's 160 times 1.5, which is 240. Okay, the rope is slowly tightened by a small massless motor which is attached to one of the objects. It is done in such a way to pull the objects closer to the center of the rotating rod. How much work is done by the motor in pulling the objects from the ends of the rod until they're 0.5 meters apart? And keep in mind they're initially 3 3 meters apart. And okay, so since there's no external torques acting on the system, I guess we could use conservation of angular momentum. So, which basically states that the initial angular momentum is equal to the final one. So initially we have the 2-point masses, and for now I'm going to use variables just because it's safer. So our initial angular momentum is going to be 2m, since there's two masses, times r sub 1 squared, where r sub 1 will be equal to 1.5 meters, since that's the distance from the axis of rotation. Okay, and then so the initial angular velocity is 4, and now our final momentum, so it says they're 0.5 meters apart. So, okay, so we have 2, the mass still stays the same, and we have r2 squared times the final angular velocity. We can clean this up by getting rid of these. So we have the final angular velocity is equal to 4 times 1.5 squared over 0.5 squared. And that's 2.25, and this would be 0.25. 2.25 times 4 is 9. So we should get that. It's 36 radians per second. And it's asking how much work is done. Well, work is just the change in kinetic energy. Since this is rotational, we can write this as 1/2 times um, 1/2 times this minus 1/2 times the final kinetic energy, and we said this is 2. Actually, I'm just gonna plug this whole thing in my calculator. Yeah, that would be a lot easier. So we said that the initial moment of inertia is 2 times m, which is 5, times r squared, which is just 2.25, and I get that right. Yeah, okay, and then times omega squared, which would just be 16 because it's 4 squared, minus now omega squared would be 36 squared, which is a huge change. But also the moment of inertia went down, and the moment of inertia would now just be 2 times 5 again, times r squared, which would be 0.25. Okay, and it's taking a while to input in my calculator. And basically, to sum up my strategy, so I basically knew that work was the change in kinetic energy, so I wanted to find the change in angular velocity. And okay, so we're getting 1440 joules. Yeah, okay, so that's should be correct answer. Shown below is a graph of potential energy as a function of position for a 0.5 kilogram object. Well, actually, there's a formula that relates the two. The force is actually negative du over dx. I mean, this exam doesn't require calculus, but this could come in handy. I don't know. We'll see. Okay, so which of the following is not true in the range where x is between 0 and 6? The object could be at equilibrium at either x is equal to 1 or x is equal to 3. And equilibrium means the net force is 0, and we can indeed see that sorry, I lost my train of thought. Okay, we can indeed see here that the net force is 0 since the slope is 0 and this is the slope. It's also 0, so this checks out. The minimum total energy for this object is in the range negative 10 joules. Yeah, this one's a little sus. I mean, it says total energy. It doesn't. Whereas this is a graph of potential energy. So I'm just gonna actually put a question mark. Okay, the magnitude of the force on the object at 4 centimeters is approximately 1,000 newtons. So this is 4 centimeters, and we said force. Well, the magnitude should be delta U delta X, and we said it's 4 centimeters, but we wanted meters, so it's 0.04. And okay, this is negative 5. And wait, magnitude of force. Oh yeah, okay, that's just slope. So we can use here is at negative, sorry, 3 comma negative 10, and okay, actually I'm gonna just I lost my train of thought. I'm gonna use rise over run, so we're gonna use these 2 points since they're at exact values. This is at 10, this is at negative 10, so the rise is 20, and then from 3 centimeters to 6 centimeters, it's 0.03. So 20 times 3 over 100 is 0.16. Okay, that is way off from, wait. Oh no, it's 20 times 100 over 3, okay. So it's 2,000 over 3, which I know is about 667 units, which is kind of off from this. I'm going to circle this, but let's see. If the total energy of the particle is 0 joules, then the object will have a maximum kinetic energy 10 joules. Well, yeah, because the minimum potential energy is -10, so that works. The magnitude of acceleration of the object at 2 centimeters is approximately 4 centimeters per second squared. Okay, so the slope here is let's see, this and this. Okay, rise over run, so that's 15, -10, so rise is 25, and run is 2, so 12.5 centinewtons, and the mass is 0.5, so that should be 25 meters per second squared. Wait a second, that's, okay, yeah, I think I'll just get back to this because it's taking up some time. Oh, okay, this is good. This is dimensional analysis. So a flywheel is uniform disk made of material with density rho and tensile strength measured in pascals, which, well, this is the same thing as pressure basically. So Pascal is just a Newton over meter squared, or in other words, it's force times length squared, and radius r, thickness h. Maximum kinetic energy per kilogram that can be stored in the flywheel. So we want our ending units to be in joules per kilogram. And let's try this since I guess it's the easiest. And they said that, let's see, alpha is a dimensionless constant, so let's just ignore that. So that gives us sigma over rho. And sigma is, they said it's a tensile strength. So pascals is just newtons per meters squared. And rho is density, which is mass over volume, which is kilograms over meters cubed. In other words, this should mean that we have newtons over meters squared times meters cubed over kilograms, and we have Newton meters over kilograms, which is actually joules over kilograms. And since the rest of these don't seem to match up, I think this should be the correct answer. Okay, what is the correct functional relation? Okay, this is actually pretty easy. This is a linear relationship, so we can say that log of y is mx plus b, and so we have something to the power of y. I'll just call it triangle. So y, or let's say the base is triangle, so y would be equal to triangle times mx plus b, and well, only one of these options even has x as an exponent, so it has to be d. Okay, a U-tube manometer consists of a uniform diameter cylindrical tube that's bent into a U shape. Okay. It's originally filled with water that has a density of, okay, why isn't my pencil work? Okay, that's why. Okay, it's originally filled with water that has a density of rho sub W. The total length of the column water is L. Ignore surface tension and viscosity. The water is displaced slightly so that one side moves up a distance x and the other side lowers a distance x. Find the frequency of oscillation. Huh. Yeah, I've never seen oscillation with water, only like springs and pendulums. That is interesting. Hmm. Yeah, I think I'll skip this one, and I'll also skip this one since it's based on the previous one. Okay, an object is launched vertically upwards from the ground with a speed of 50 meters per second, bounces off the ground on a return trip, with a coefficient of restitution given by C sub r is 0.9, meaning that immediately after the bounce, the upward speed is 90% of the previous downward speed. The ball continues to bounce like this, but as the amount of time the ball's launched around finally comes to rest. Assume that collision time is zero, the bounce is instantaneous, treat the problem as ideally classical, ignore any quantum effects that might happen for very small bounces. Hmm. So it's asking to find the time it takes for it to come to rest. And I think we can sort of make this into a series. Well, first of all, let's find how much time it takes for its initial trajectory before its first bounce. And the formula for that is 2 v naught sine theta over g. And since it's launched straight up, theta is 90, and it's launched at 50 meters per second, g is about 10 meters per second, so we get, initially it's 10 seconds. And from this formula, we can also see that time is directly proportional to velocity. So when the coefficient of restitution is 0.9, that means that the time of the next bounce will also be multiplied by 0.9. And so we actually have a geometric series where the ratio would be 0.9. And the formula for the sum of an infinite geometric series is actually just a sub 1 over 1 minus r, where a sub 1 is the initial value. So that gives us 10 over 1 minus, and I said r was 0.9, so that's 10 over 0.1, which is 10 times 10, which is 100 seconds. So this one it actually isn't too bad as long as you know the formulas. Yeah, I do not like graph problems, but okay, what's this? A 2 kilogram object falls from rest a distance of 5 meters onto a 6 kilogram object that is supported by a vertical massless spring with spring constant 72 newtons per meter. Two objects stick together, blah blah blah. What is the maximum magnitude of displacement of the 6 kilogram object from its original location before it is struck by the falling object? Okay, so I'll just draw it out. So we have our 2 kilogram object, and let's just say that, okay, that's terribly drawn, but that's our spring, and we have our 6 kilogram object, and they are 5 meters apart. And this is implying that it's compressed, or the 6 kilogram object was compressed before the collision. And yeah, okay. I guess there's several approaches to look at this. I think we could use momentum. Yeah, okay, so Let's see if we can use momentum for this problem. Falls distance 5 meters. Well, actually, no. Okay, so it falls the distance 5 meters, but we don't know if. But then the mass attached spring is also released, so I'll just say it's here now, and so it goes this far. Okay, so let's first look at momentum. So we know that the initial momentum is 0 since they were held at rest, and there were no external forces acting on the system. Well, other than gravity, but gravity was acting on both of them. I think, yeah. Okay. So then, then the final momentum must also be 0. Okay, so there's also another formula, so V is equal to square root of 2gh, and we can use that to find the velocity of this during collision. So, yeah. So we plug in, it falls a height of 5 meters, so we have 2 times 5 times g, which is also the square root of 100 if we use 10 for g, which is 10 meters per second. So then there's a momentum this way of 20 Newton meters per second. And this is 6 kilograms, and to cancel out that momentum, we also need 20 Newton meters per second this way, but the velocity has to be a third since the mass is 3 times. So then the velocity would be about 3.33 meters per second. And yeah. Oh, okay, and then now I think we can actually use energy. So initially when it's compressed and it's at rest, the energy was 1/2 k, well, in this case delta y, uh, k delta y squared, and which is equal to 1/2 m, and then it was 3.33 squared. M is 6 kilograms, and we want to find. Okay, we want to find delta y. So we can actually also get rid of 1/2, divide by k, which they say is 72, and then the square root of this. So delta y is equal to, we can take the 3.33 out, so 3.33 times the square root of, well, we can reduce this to 1/12. Okay, so 3.33 times 1 divided by 12, and we get about 0.96, which is closest to B. Yeah, it's probably a little off because I might have done some rounding with the 3.33, but it's definitely closest to this, closer to this than the other ones. Okay, and yeah, I do not know how to do this one. Let's see if I can do this one. Determine the ratio of omega sub 1, or omega sub 2 over omega sub 1. That is a good question. And it says they will oscillate exactly out of phase. And yeah, okay, to be honest, I'm not sure how to solve this one because it, I'm not really a big fan of oscillations, so I should definitely prepare for oscillations. But yeah, I think I'll probably have to guess on this one. Hmm. Hmm. Okay, let's see. A solid ball is released from rest down inclines at various inclination angles, theta. So, theta, we have some solid ball released from rest. The coefficient of static and kinetic friction on ball equal mu, which in bond graphs best represents total kinetic energy of the ball at the bottom of the incline as a function of the angle of the incline. Okay, interesting. Well, we know that, uh, huh. Okay, so actually let's just draw a force diagram. So we have mg, and then we have the components of mg that are both perpendicular and parallel. And then we have the normal force, which I do not think is needed for this one. And then we have friction, which is mu is the same for both kinetic and static friction, so and it's just equal to mu mg cosine theta. And then this is theta since it's a similar triangle. Then this is mg sine theta. And yeah, okay, mg sine theta. Okay, so then the forces that are parallel to the incline are mg sine theta and this. So the acceleration would be g sine theta minus mu naught g cosine theta. And then since it starts at rest, the velocity as a function of time would be sine theta minus mu naught cosine theta times gt. Hmm. Yeah. Sine theta minus. Yeah, okay, I'm not quite sure. That's no idea how to do that. Okay, yeah, let's just do this one since I was kind of close to solving it anyways. Okay, so the object is 0.5 kilograms. And yeah. Okay, the magnitude of acceleration of the object at x equals 2 centimeters. So here is approximately 4 centimeters per second squared. Okay, so we can, I guess, sort of find the slope here. So using this point this point, so it goes down by that's 15, 25 joules, and the run would be 2 centimeters, or let's make that 0.02 meters. 25 over 0.02, and that would just be the force, but the acceleration would be the whole thing over the mass. Okay, 25 divided by 0.02 is just 25 times 50, so 1250 over the mass, which is 0.5 kilograms, so 2500 meters per second squared. That does not sound right. Hmm. Yes, I think actually then, since that one is way off, this should be an answer. Let me double check this one. So the object at 4 centimeters. Hmm. Slope is about 1. Wait, no, okay, 4 centimeters. So here is 10. Here is 0. Here is 10 over 0.01. 10 over 0.01. Actually, I can see how. Okay, so this would be 1,000 newtons. So actually, this is correct. And yes, and this is way off, so this is E. And are there any others that I left blank? Okay, I also left this one blank. Which of the following statements about the pendulum bob's acceleration is true? Okay, so we narrowed it down to C and E, and magnitude acceleration is 0 at some point in the pendulum swing. Okay, so if I draw the full, let me draw it like this. Trying to see where it would be 0. Well, the velocity would definitely be 0 here and here, but I don't see the acceleration 0, so I think this one's E. Okay. Yeah, not sure how to do that one. Okay, I have a little over 10 minutes left, but I think I'm just gonna guess the remainder of the questions. Uh, well, there weren't any external, so look this again. There weren't any external forces acting on this, and I don't think there was any energy that was transferred from outside the system, so change in kinetic energy should be negative, if not zero. I never said it's elastic, so I'm just gonna go with it's being negative. Okay, and then yes, I'm just gonna guess the main questions and I'll see what I got. Huh. Actually, let's see if we can think about this. So okay, so obviously we know that the kinetic energy should increase as well. The flatter it is, the lower the kinetic energy would be. So wait, um, actually no, because the vertical height would be fixed. So then yeah, I think I'm gonna go with. Well, it's definitely not E because it can't be 0 at 90, and well D looks. I'm gonna go with either A or B. Okay, I'm leaning towards A. That too. Okay, guess we'll be checking answers. And usually the cutoff for this test to make it to the next round is like 15 to 17, so I hope I'm near there. And these are the solutions. So let's okay, so far I know I got this one right, so that's one. I got this one right as well, so that's two right, three right. Did I get that one right? Okay, four right. Nice. Five right. Six right. Seven right. Eight right. Oh wait, I did not get that one right. Okay, so we're still eight right. Yeah, okay, I got that one right. So it's nine right. Not bad. 10 right. 11 right. 12 right. Oh, I think I put 240 for this one. Oh, because it's. Oh, yeah, I should not have doubled it. Okay, so. What was that? 12. Okay, so 12 right. 13 right. Um, yeah, okay. 14 right. 15 right. 16 right. That one was wrong. Okay. Guess that one. Let's see. What was it? Oh, 17 right. Okay, that was a lucky guess. 18 right. Nice. Okay, this one's wrong. But yeah, 18 right, 19 right, not bad. Okay, still at 19 right. And okay, so overall not bad. I mean, it's definitely above the cutoff, and I guess I managed to do it on time. So 19, and yeah, so that is my run through of this exam. And currently now, even after grading, I have 5 minutes and 7 seconds left to spare. So overall, my pacing was definitely not bad, and yeah, thanks for watching, and I hope you enjoyed this video. And peace.